be the tension that outweigh weight in order to achieve acceleration going upward. You agree with that statement?
Yeah.
So now that we know that, what do you think we need to calculate? All right, so what do we need to be thinking about? What's the big picture here? What have you not? Free body diagram is the first step of what? What's the next step we have to do? Do Newton's law, and we're going to have to do, because it's at the first law would be if it's at equilibrium, right? Second law is actual motion, because the sum of the forces do not equal zero. Okay. Here, the sum of the forces will equal zero. Here, the sum of the forces don't. They equal what? Mass times an acceleration. Newton's law. So what we need to do is figure out what the sum of the forces are. In this case, because it's purely vertical, we're going to have the sum of the forces in which direction? Up and down, right?
Yes.
So that's the y direction. So what are the forces we have in the y direction?
We have tension and weight.
Okay. Which one of those is acting in a positive direction?
Tension.
Okay, so we're going to write tension minus weight. Okay. And then that's going to equal the mass times acceleration. We're moving. Had we not been moving, the sum of the forces would have been zero.
Right.
You understand so far?
I understand.
What is the weight?
Weight is mass times gravity, which has a constant acceleration.
Good. And when I'm using mass here, what am I speaking of? Is it the mass of the chain? Is it the mass of the boulder, or is it the mass of both?
It's the mass of both.
Good. So it needs to be a total mass, which would be the 750 plus the 575.
I got 1325.
So that's the mass total. So what do we do now? What is the SI unit for force?
The units for force are kilograms times meter per second squared.
Otherwise known as?
Newton.
Good. All right. What's going on with this tension over here? What do we do there?
Tension, let's see. Tension exists in the chain alone.
I said, uh-huh.
So it's supposed to be less than or equal to 2.5 W, the weight. And the weight is the mass times gravity.
To solve for A, so if you were to multiply that out and then divide,
you get about 0.83 meters per second squared.
832, good. You understand?
I understand.
We have a part B to the question. How long does it take to get lifted out at maximum acceleration if we start from rest? So, what are your thoughts on that? We're looking for a time frame now.
So if we start at rest, that means initial velocity is 0.
Good.
And we're only lifting it up, which means that we're going to need, we know distance.
The key word is the constant acceleration.
And we know acceleration.
Yep. You should have gone through a bunch of equations that had constant acceleration in chapter 3, right?
Yeah, we did.
One of them said the change in distance equals the initial velocity.
Change in distance equals initial velocity times time plus 1/2 of acceleration times t squared.
You got it. Okay? So what we got to do is, well, we know it's purely y, so this is going to be delta y. This is v naught y. And we have, because it's not gravity, right? It's,
yeah.
We've already accounted for that gravity.
Yeah.
Problem. The 17.832 from the last problem. Good. Good job. So then multiply both sides by 2, divide by 0.832, the square root it, you should get 17.
17.33.
Got it?
Got it.